All right, welcome everyone to week 11 of our biochem reviews. So week 11 is, let's see, we're learning gluconeogenesis. We start talking about the kind of reciprocal regulation from the metabolism unit of the kind of the pathway and its reverse. And then I believe you guys have your exam either tomorrow or next Tuesday. So we're going to do a short little review of kind of the main topics of this unit. So I'm just going to go ahead and jump right in to give you guys time if you have any questions at the end as well. So the first question I have here is, why is gluconeogenesis necessary? So this is something that I personally got really confused by for a really long time. This is something that I think can be really weird to think about because, well, if I've consumed this glucose, the sugar, why can't I just use it to power me? Why do I need to make more glucose when isn't that just wasting energy? And the answer is kind of yes, but more so it's about where the energy is. Right, so we have to consider location. And I'm not going to throw numbers in, although I could, but specifically when I say location, I mean the brain. Glucose can enter the blood-brain barrier. Pyruvate cannot. Any of the charged molecules that end up happening, anything with phosphate groups, etc., cannot go through the blood-brain barrier. And so as a result, if the brain needs energy, which, I mean, it uses about, 20% of the body's daily energy anyway, so it usually does. If the brain needs energy, we can't just transfer some pyruvate in there. We can't just transfer whatever. It has to be glucose. So if you've been exercising, let's say, and then you stop exercising, well, when you've stopped exercising, your body is, for some small period of time, still doing glucose because it hasn't really caught up with it yet. So it's still doing glucose, it's still doing glycolysis, excuse me. It's still doing glycolysis. And then as soon as that catches up, it realizes, wait, now I have too much pyruvate in the muscles, which I don't need anymore, and I don't have enough for the brain. So what happens? Pyruvate is converted back into glucose. And then when it's converted back into glucose, it can it can go into the brain, pass the blood-brain barrier, give your brain energy. The other reason this can happen is when you have a low blood sugar. If you use too much glucose, low blood sugar, sorry, let me write that down. Yeah, so if you use too much glucose, then you're going to need to, then your blood sugar gets low and your liver reacts. So gluconeogenesis occurs in the liver specifically. And remember with the enzyme we talked about, glucokinase as opposed to hexokinase. And so when you have low blood sugar, one of the enzymes, and I won't say which one because there's a figure about it later that I think will help, realizes that your body needs more glucose, and so it triggers gluconeogenesis and inhibits glycolysis. Okay. All right, so the next question asks, glucose is often described as almost the reverse of glycolysis. Excuse me, that's a typo. Glycolysis. Why is the almost necessary? So this word almost is one that you're going to hear quite a lot when it comes to these reciprocal reactions. Is they're almost the exact same, but not exactly. They're almost the reverse, but not exactly. They're almost, right? And the answer comes down to energy. When we look once again at those three very exergonic reactions, reaction 1, reaction 3, and reaction 10. These are exergonic for kind of a few reasons. The reason these two are exergonic is because they are coupled to ATP hydrolysis. ATP hydrolysis. And this one is very spontaneous because of the whole thing with the keto and enol forms and the tautomers, I don't know how to say that, excuse me, and how that just really boosts stability. It's very difficult to do the reverse of these reactions. 1, 3, and 10 going in reverse is very hard, nearly impossible, because they're so exergonic. Reaction 2, reactions 4 through 9, yeah, they can go in reverse anytime. Those are fine, they're not the problem at all. But we need to do something weird when it comes to reaction 1, when it comes to reaction 3, and when it comes to reaction 10, okay? And so just based on this diagram, without me saying a word about any of the details, you can tell me right now that the reaction of, well, reaction 2 is glucose 6-phosphate, and that's isomerized into, and I'm going to start abbreviating, fructose 6-phosphate, F6P. I can tell you the reverse reaction of F6P to G6P, which is this glucose 6-phosphate, is okay. Like, these reactions are going to be catalyzed by the same enzyme, and they're both okay happening just depending on concentration, right? So yes, this reaction is slightly exergonic, like maybe -3, -4, -5-ish kilojoules per mole, but it's not -35, it's not -20, it's not -25 like the other reactions. And so because of that, reaction 2 could happen spontaneously in the reverse reaction, but the net of glycolysis, reactions 1 through 10, could not happen spontaneously. Reaction 2 can happen in reverse easily. 4, 5, 6, 7, 8, and 9 can. 1, 3, and 10 cannot. Okay, I know that I'm kind of harping on this, but this is a really big topic, and it really does explain kind of everything going on in the body in some ways. Okay, so the three reactions in again, I apologize, I don't know what came over me when I was prepping this. Glycolysis that are not present in gluconeogenesis are catalyzed by the following enzymes. How does gluconeogenesis reverse these reactions? So, as you can tell, the three reactions are the hexokinase, which takes glucose plus ATP in the reactant side, and it converts them to glucose 6-phosphate or G6P and ADP. Okay? So, how do we undo this reaction when it's so spontaneous? And kind of the real answer is we don't. And I know that's not a satisfying answer, but the truth is we have to use a completely different enzyme. It's nearly impossible to just undo it when it's so spontaneous. And so what we do is we're going to take, and I'm going to use a different color. I'll use red for gluconeogenesis. We're going to take G6P and water, and using a completely different enzyme, in this reaction, it's going to be, I believe, G6-phosphatase, as it's called, or glucose 6-phosphatase. Glucose 6-phosphatase. There we go. We're going to create glucose and inorganic phosphate. Okay, so I want to point out the key differences here. In the forward reaction, we're using a kinase. In the reverse, we're using phosphatase. That makes sense. Kinase attaches, phosphatase removes. Cool. All right. Then there's this weird, oh, did not mean to do that. This weird thing. We're taking ATP to ADP in the forward reaction, but then we're using water and inorganic phosphate in the reverse. Let's pause for a moment and ask why this is the case. Okay. So I can tell you all, once again, I've used this number quite a few times in the past. ATP hydrolysis is exergonic. And specifically, the reaction has a delta G prime, so biological conditions, of somewhere around -30.5 kilojoules per mole. That's a very big negative number. Okay, so to do the opposite, so ATP synthesis, and I should clarify from ADP, is logically the opposite of this number. Therefore, its delta G value would be positive 30.5 kilojoules per mole. Okay? In other words, in order to remake ATP substrate level, obviously we make ATP later on through the electron transport chain, but we'll get there later. In order to make ATP here at a substrate level, we would need to put 30.5 kilojoules per mole of energy into this glucose 6-phosphate. And that is way too much for the body to handle. Okay, so what the body does is it uses an esterification, or an ester hydrolysis reaction. And effectively what it does is it removes the phosphate group. So if you all remember, the phosphate group attaches on the 6th position. So the 6th position is the one sticking out. So you've got this and then the rest of the ring, which I'm just going to draw very quickly. And you have CHO and then O, O, and O. So that's the phosphate group. All we do, excuse me, I don't know why that happened, is we put this OH in here and we get CHOH basically. Okay. So let me highlight that. This bit right here becomes this bit right here. Okay, nothing else changes. But what this does for us is this is a fairly simple reaction that kicks off phosphate as opposed to needing 30 kilojoules per mole of energy, because that's way too much for the body to afford every time it wants to do gluconeogenesis. Okay. Now there's a couple of other weird aspects of this, but for now I just want to focus on the actual reaction mechanism that's happening. Okay. So that said, let's go to the next reaction, phosphofructokinase. Now I hope we're all okay with this reaction because it takes fructose 6-phosphate to fructose 1,6-bisphosphate. Okay, and I'm going to specifically clarify, we're talking about PFK1. Okay, this is a question that you might have had about from last week. PFK1 is phosphofructokinase 1. It phosphorylates fructose 6-phosphate in the first position. There's another PFK about it in a little bit that phosphorylates in a different position. Okay, and we'll get there, but I just want to make sure that we're clear. This is PFK1. PFK1 is the one involved in glycolysis and in gluconeogenesis. Okay. Now, once again, it uses 1 ATP, and we get out 1 ADP. Okay. So it may not surprise you all. The reverse reaction is pretty similar to the reverse reaction we just talked about. In fact, if you just change the numbers of the glucose and the fructoses, it's basically the exact same thing. So switching to red, we start with, once again, F16BP, and once again, H2O. And I've kind of limited myself on space, so I'll just do it like that, I guess. We go to F6P plus, once again, inorganic phosphate. Okay, and I did that one in red as well, so let's keep red. And the enzyme that that catalyzes this dephosphorylation is, if you all could guess, oh, I don't know why I didn't switch to red, there we go, is fructose 1,6-bisphosphatase. Phosphatase. In other words, it's quite literally the exact same thing. You take the name of the thing, fructose 1,6-bisphosphate, glucose 6-phosphate, and add the ACE to it. Okay? ACE and ACE. Okay? All right. Now, once again, we're looking at ATP to ADP. We're looking at water to inorganic phosphate. The exact same thing is happening here for the exact same reason. Your body cannot afford to give away 30 kilojoules per mole of energy every single time. Not even every single time it wants to do gluconeogenesis, every single time it wants to do a step of gluconeogenesis. And so it says, scrap it, we're not going to try to remake the ATP, let's use up some energy. It's okay, all right? So I also want us to think about these reverse reactions in terms of energy. We used 2 ATP in glycolysis to get a total of 4 ATP out, or a net gain of 2 ATP. Here, we're saying ignore the ATP, we're not going to try to get energy out of it, we're okay with it. And in the next step, you're going to see we're actually going to lose energy in the pyruvate to get back to phosphoenolpyruvate. We're going to lose energy. Why? Because we're not doing this to gain energy, we're doing this to get the energy where it needs to be. Okay? Right. So I've mentioned the pyruvate reaction. And I guess I should reword that because it's not the pyruvate reaction, it's the pyruvate reactions. In other words, there's 2 of them. And the reason there's 2 of them is because partly location, partly just kind of, it's the easiest way to do it for the body. Okay, so we're going to talk about the first reaction. Okay, there we go. So pyruvate kinase is, once again, the forward reaction, taking phosphoenolpyruvate, and converting it to pyruvate. and we have a plus ADP plus ATP, right? Okay. So the reverse of these reactions, or I'm sorry, the reverses of this reaction, flip the plural, is we take pyruvate. Once again, I need to do this in red. Give me one moment. Pyruvate, we convert pyruvate to oxaloacetate. Oxaloacetate. The enzyme catalyzing this reaction is called pyruvate carboxylase. Okay. Pyruvate carboxylase. Okay, so let's talk about this pyruvate carboxylase reaction for a moment. Okay, this reaction uses, I'm going to say ATP. It uses ATP. Okay, why does it use ATP? Because effectively what it now needs to do is, let's look at the word carboxylase. Okay, we're effectively adding a carbon dioxide, or bicarbonate, your professor might say. So what we're doing, and I'm going to switch colors, we are saying pyruvate is 3 carbons. We're going to add CO2, or the conjugate base of, or the conjugate acid, excuse me, of CO2, which is bicarbonate. Effectively, we're going to add a carboxylate group, and that's why the name is what it is, to get a 4-carbon oxaloacetate. Okay, so this 4-carbon oxaloacetate here, this uses ATP. ATP to ADP, right? Let's once again pause and think. I told you all, we are not caring about energy right now, okay? One is catabolic, one is anabolic. Glycolysis makes energy, gluconeogenesis uses energy, okay? We don't care about using ATP right now because there's something more important, okay? So we're at oxaloacetate, that's great, okay? Oxaloacetate then, and I'll switch back to red, is converted into PEP, which I'm going to abbreviate for convenience, phosphoenolpyruvate, excuse me, right? Now PEP, or I should say this reaction is catalyzed by the enzyme PEP carboxykinase. Carboxykinase. Okay, so let's split that word up for a moment. Carboxy is that same thing as right here, so we're adding or removing a carboxylate. Fine, that makes sense. Kinase. Once again, energy, energy, energy. In this case, the energy is not coming from ATP. And this is a little bit of a weird one. The energy is actually coming from GTP. Plus GTP here gives you, oh, I guess I should have done it this way, huh? GDP here. Now, I'm going to go ahead and kind of amend the statement that I put up here of ATP. I'm now going to say XTP, with X being any of those nucleotide bases. So ATP, GTP, UTP, and CTP. There we go. And that's going to have very similar delta G values of about negative 30.5 kilojoules. All right. It's not going to be perfect, but they are fairly comparable because they all have that same high energy phosphate bond, or a phosphodiester bond. Okay. So we've now used the equivalent of 2 ATP. And let's think about what we did. Is we also now released CO2. We used CO2 in the first step, which I did not mention, plus CO2, and now we've released it. Okay. I don't really get why is a very common question, and the short answer is basically, and that comes down to location, which I'll show you guys in a little bit. But effectively, what we're dealing with here is using 2 ATP, which is the net gain, in order to go all the way back. Okay, so energetically, we get a total of 2 ATP from gluconeogenesis. Here we use 2, but we don't just use 2. That's the thing. We use 2 per pyruvate, but there's 2 pyruvate to 1 glucose. Therefore, we used 4. Okay, so glycolysis is plus 2. We're so far at minus 4. We'll see how the rest of it is changed, but right now, let's just keep that in our mind. This took 4 ATP, or 4 ATP equivalent, I should say. Okay? All right. Now let's look at the actual reactions kind of overall. And this is what I keep talking about location with. So this reaction, or I should say, so we know pyruvate goes into the mitochondria in order to continue on the tricarboxylic acid cycle, citric acid cycle, whatever we want to call it. And then from there, it goes through the electron transport chain. One of the intermediates of the tricarboxylic acid cycle, of the Tca cycle, is oxaloacetate. Okay, this is an intermediate of the cycle. Therefore, again, thinking about the compartmentalization we talked about, it must have been 2 weeks ago. When you have high concentration of oxaloacetate, that oxaloacetate leaves the mitochondria and can be converted into phosphoenol pyruvate. So why would you have too high a concentration of oxaloacetate? The answer to this could be kind of anything. The first, or not anything, but the answer to this with respect to what we're focusing on here is if I made too much pyruvate and either I can't take the, I can't go into the electron transport chain, or something or another is going on, but I just have too much oxaloacetate because of too much pyruvate, that's a great sign that I now need to get rid of some of my pyruvate and turn it back into glucose. Okay, so we're going to go reverse of what we've been learning, forward in terms of gluconeogenesis. So I'm going to be talking opposite of glycolysis. So starting with pyruvate, we've converted to oxaloacetate. Oxaloacetate can now leave the mitochondria. Sorry, these are the enzymes. So pyruvate carboxylase converts pyruvate to oxaloacetate. When oxaloacetate leaves, it using pyruvate carboxykinase gives us PEP. Then the reactions from this up to glyceraldehyde 3-phosphate. So this was made in reaction 9. So reaction 9 to reaction 8 to 7 to 6 to 5, all the same. So this is made in 5. And then once again, reaction 5 to reaction 4 to reaction 3 are all the same. This is where we get weird. Going the reverse of reaction 3, once again, the forward reaction uses phosphofructokinase, the reverse, fructose 1,6-bisphosphatase. Okay, and we get to fructose 6-phosphate. Reaction 2, the reverse of it is the exact same, which is why you see double arrows as opposed to 2 separate arrows, and that's the same with all of those. Then glucose 6-phosphate to glucose needs glucose 6-phosphatase. Okay, so location. Now, why is it so important? Is it governs concentration, right? If the mitochondrial concentration of pyruvate is really high, and I want us to think about mitochondria as energy. So pyruvate will, I've said this probably 12 times, pyruvate is the most connected metabolite. If pyruvate is going into the mitochondria, it's going there for energy. If it's going somewhere else, it might make amino acids, whatever, but for the most part, pyruvate in the mitochondria, energy. Energy, energy, energy. Therefore, since pyruvate in the mitochondria is going for energy, I'm going to think of it as almost like an energy unit. Okay, so we have 5 units of pyruvate energy, 10 units, whatever. When you get too many, your body says, we're just wasting the glucose. Let's go to oxaloacetate and go backwards so that we can get energy. Okay, so governing concentration, concentration ultimately governs which pathway we follow. Which pathway? All right. Then the second reason is I just told you all oxaloacetate is naturally present in the mitochondria. And I'm not going to go into the Tca cycle too much because that's not on this exam and I don't want to distract you all. But the Tca cycle effectively has oxaloacetate plus the acetyl-CoA, so what pyruvate becomes, acetyl-CoA into citrate, and then citrate goes through a few reactions, blah, 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 blah. Then we get malate, and then malate is converted to oxaloacetate. So the importance of us being in the mitochondria is the presence of oxaloacetate, because then we can say high concentration of oxaloacetate means that our TCA cycle, our citric acid cycle, is stuck. It's not moving, and we're not depleting our oxaloacetate. Therefore, we have too much going on. Get it out of here as PEP, or like get it out of here, convert it to PEP. Okay? So that's why location is really important, especially with pyruvate, but also with oxaloacetate. Okay? However, oxaloacetate cannot leave the mitochondria. Okay? So this is arguably one of the most bizarre things that I think it's just so weird. It doesn't really, I don't like it very much. But effectively what we do is, I pointed out malate here for a reason. Okay? And the reason is oxaloacetate leaves as malate. Okay? So here's what I mean by that. And I'm sure you've seen this figure in your professor's slides or in your textbook. It's a good figure. Okay? Pyruvate enters the mitochondria. Cool. Pyruvate is converted to oxaloacetate. Makes sense. We just talked about that. Oxaloacetate is converted to malate. Okay? Malate leaves the mitochondria and then is converted back to oxaloacetate. Okay? So I want to point out the reaction that governs oxaloacetate to malate, malate to oxaloacetate, energetically neutral, we don't really care about it. We use one NADH, we get one NADH. Doesn't matter. Okay, that's why we're glossing over it. We'll be talking about it with the TCA cycle anyways, not on this exam. Okay, then oxaloacetate can be converted to PEP for the sake of gluconeogenesis. Okay, this is weird. I don't like it. I don't think it's very intuitive, but we have to keep that in mind. It's malate that leaves the mitochondria. Okay. Oxaloacetate is the one that we focus on because oxaloacetate is, like I said, it's the thing that reacts with acetyl-CoA, with effectively pyruvate, or like the product of glycolysis. So if there's high, and I'm going to abbreviate oxaloacetate OA from now on, if there's high OA, that means that there's that the TCA cycle is kind of like, it's either not working or it's working so much that there's just a buildup, like buildup of intermediates. And I guess I shouldn't say is, I should say has a buildup of intermediates, therefore too much. Therefore, go backwards. Okay, but we're not just going to go backwards because that would just kind of defeat the purpose. We just have energy floating in the mitochondria, nothing else. So we go backwards all the way through gluconeogenesis. Okay, I think it's a weird topic, but you have to know it, unfortunately. Okay, the next question I ask is, how can oxaloacetate be converted into phosphoenolpyruvate? Okay, now I talked about the mechanism earlier, but there's a reason that I ask this question the way that I do. Okay, the first part of this reason comes down to, once again, CO2. Keep track of CO2. It is not something we normally keep track of, but it's going to come up again in terms of carbon number. When we add carbons and remove carbons, that's using CO2 for the most part. And, here's actually, let me show you all the actual structures. Okay, so here is the reaction of oxaloacetate to PEP. I forgot that I had this here, I apologize. So once more, I want to reiterate the fact that PEP is really unstable because you have this oxygen, which is acting as the alcohol in this case, and then the double bond, which is causing this enol, right? Hence phosphoenol pyruvate. This is unstable. So how can it be converted? First, the use of GTP to catalyze the reaction, or like coupled with the reaction, really helps it. Second, when we keep track of our carbons, we see this is 4 carbons and this is 3 carbons. Therefore, CO2 is released. Okay. So CO2, once again, not the most concerning thing in the world at the moment. But once you get into the next unit, it's something to really keep track of. And the next unit, I mean, we're nearly done anyways. So really Thursday or next Monday or next Tuesday. So we're getting very close. So yeah, so that's this reaction. Okay, so this is where things get very complicated. So the regulation of phosphofructokinase, or once again, PFK, is, or I should say, generally speaking, regulation is not something that I spend way too much time on, because regulation generally makes sense. When you have too many of the product, you inhibit it, the forward reaction stops happening. Easy enough. PFK is very, very regulated for a whole host of reasons, and we'll talk about the main two now, but it's regulated using basically PFK2. Okay, so I'm going to be very mindful of the words and numbers. There is a phosphofructokinase 1 and there is a phosphofructokinase 2. And I mentioned they just phosphorylate in different positions. We're going to get into that later, but I really just want to pause and make sure that I'm clear about that. Okay, so the reaction catalyzed by PFK is regulated as it's the committing step, right? So as soon as you hit reaction 3, and yes, obviously you can do gluconeogenesis, but as soon as you hit reaction 3, this fructose 6,1,6 bisphosphate, I should say, is committed to going all the way until it reaches pyruvate. Okay. Therefore, since the forward is really, really heavily regulated, the reverse also needs to be really heavily regulated. Okay. So I'm going to give you guys the basic ones first, because the basic ones are, we'll just get them out of the way, and then we're going to go into a figure and we're going to get into the complicated stuff. Okay. So first, this is activated. So I guess I should say the enzyme. So fructose 1,6 bisphosphatase, and I'm gonna say that to say this is the enzyme. Okay, it is activated by citrate. Okay, citrate. All right. Now I'm not expecting you all to know the Tca cycle yet, but citrate is right here. It is the first product of the Tca cycle that is made. Oh, jumped way too far ahead. I apologize. So in other words, think of citrate as the reactants of the Tca cycle. If there's a lot of reactants, that's telling us we have way too much, stop making more, and so therefore we're activating the gluconeogenesis enzyme. Okay? Then it's inhibited by F26BP. Okay? Now keep the number in mind. 26BP, not 16. Okay, this is 2 and this is 1. And I might try to do them in different colors or highlighting later to keep it clear, but I want to point out that those numbers first, right? It's also inhibited by AMP. Okay, and we're going to get into F26BP later. For now, I want to focus. AMP, once again, is telling you low energy, right? ATP equals we have energy, we're good, stop working. Okay, AMP says we need energy. We need energy. All right. So it makes sense. Gluconeogenesis is basically saying stop making energy, go back to glucose. So it would inhibit, sorry, hang on, let me repeat that. AMP says we need this energy desperately. Why are you stopping and going in the reverse direction, right? That's why AMP inhibits the gluconeogenesis side of this reaction. But guess what? Citrate we talked about last week. Oh, citrate we talked about last week. Citrate inhibited PFK1. And F26BP, AMP, they both activated PFK1. Okay, and that leads into the next question, which is what is this type of regulation called and why is it important? This is called reciprocal regulation. Okay, so I want us to think of reciprocal regulation. So reciprocal is, opposites, and regulation is regulation. So the steps that are not in common all have this reciprocal regulation. Because let's think about it if we didn't have it, okay? So in other words, if both F16BP and phosphofructokinase, PFK1, were active at the same time, we would be using energy to make F16BP and then immediately converting that F16BP back into F6P without making any energy back, mind you. And then we would take that F6P that was just made, and then using PFK, we would make more F16BP and so on. And so these steps are really important because these are where we say, shut down gluconeogenesis, we need to do glycolysis or the opposite. These are the steps where we can really make sure that we're not wasting a ton of energy for no reason, okay? So that's why it's important. All right, now number 9. This is the diagram that I meant that is just kind of complicated and big and excessive. I personally love this diagram. I think it does tell the story well, but it needs a few minutes to explain it. Okay, so we don't start at the top. Or you can start at the top. I don't like starting at the top. I start here. Okay. Oh, by the way, the question here, I forgot to ask it, is what is the role of PFK2 or phosphofructokinase 2 in glycolysis and gluconeogenesis? So once again, PFK1 is what we've been dealing with. It adds in the first position, hence the 1. PFK2 is the new one that I'm telling you all about that I mentioned briefly last week. It adds in the second position, okay? So I'm going to do my best to keep them as separate as possible, but I apologize if I misspeak, and I'll do my best to correct it, okay? So when you have, so like I said, we're starting with this F6P that I highlighted. When you have high concentration of fructose 6-phosphate, that tells the body to activate PFK2. So now PFK2 is active, and PFK2 triggers the forward reaction of F6P to F26BP. So the forward reaction is now happening, and we're making more of this. That, in turn, causes the red arrows around the sides to happen. So that will activate PFK1 and inhibit fructose 1,6-bisphosphatase. Okay, so let's just think about what I've just said. It's activating the glycolysis version and inhibiting the gluconeogenesis version. In other words, it's saying shut down gluconeogenesis, activate glycolysis. And why is it saying that? Because we have a high concentration of fructose 6-phosphate. That high concentration is a sign that we need to get some glucose out, okay? Because you only have a high F6P concentration when you have a high G6P concentration, and you only get that when you have a high glucose concentration, okay? So that activates the forward reaction of F6P to F16BP, and then glycolysis happens. Glycolysis happens, okay? All right, so that's the left side of the regulation. Let's look at the right side, okay? So I'm gonna do my best once again to change colors. So low blood sugar now triggers glucagon, okay? Glucagon, glucagon, insulin, they're polar opposites. Well, glucagon is now going to phosphorylate PFK2. So phosphorylating PFK2. And I said I was going to change colors, and I did not. I will use green for the rest of this. So PFK2 is now phosphorylated, which means it is inactive. Okay? In other words, we are shutting down the forward reaction phosphorylating F6P. And I don't want to say we're going to go back to this, but equilibrium is no longer going to favor the forward reaction as much. Therefore, you will have less F26BP, okay? You will have less of it. Now that has ripple effects, because when you have less of it, you activate glycolysis less. You inhibit gluconeogenesis less, okay? And in turn, that means that you're basically taking down PFK1 and bringing up F16BPase, okay? And then what does that do in turn? That inhibits the forward reaction because we've decreased PFK1 activation, and that triggers the reverse reaction, which then gives us gluconeogenesis. All right, so in other words, presence of PFK1, or I should say, let's start with the things that actually govern this. So F6P, when you have high concentration of F6P, that's an indicator that you have a high glucose concentration, which tells you want to do glycolysis, or in other words, or some other pathway, like the glycogen ones, which we're not talking about right now, but you want to do glycolysis in order to get rid of your high blood sugar, okay? When you have a low blood sugar, you want to do the opposite and you want to raise your blood sugar. How do you raise your blood sugar? By converting all of those intermediates that you have, the pyruvate and stuff like that, back into glucose. So F26BP, fructose 2,6-bisphosphate, is the key to this reciprocal regulation, okay? Yes, citrate, AMP, ATP, they play their own roles and they each regulate, but fructose 2,6-bisphosphate is arguably the most important part, and it's really what's governing the activation and inhibition of these pathways, okay? That was complicated. I know. I'm going to take a breath and I'm going to make sure I'm going to pause for a moment to see if there are any questions. So please, if you have any, feel free to ask them. Primarily about this, I'll have some general time for questions about the entire unit in a little bit though. Okay, so it doesn't look like there are any questions, so we're going to move on. Okay, there we go. So, apologies, technical difficulties. Okay, so let's look at the entire kind of pathways. So I'm going to start with glucose to pyruvate, and then I'm going to go pyruvate back up to glucose. Okay, and we're going to talk energy as soon as we hit this. And I don't know if okay, never mind. Yeah, so we're going to talk about energy in this section. Okay, so glycolysis, we're going to use 1 ATP straight away for glucose to glucose 6-phosphate, then another, and I'm going to go through glycolysis pretty quick since we're confident about that, another to phosphorylate fructose 6-phosphate. Then we get 2, because remember I have 2 in them, because fructose 1,6-bisphosphate breaks into 2, well, G3P and DHAP, but effectively that becomes 2 G3P. So all of this is with 2's in it, including the NAD plus and NADH stuff, right? Then we get another plus 2 ATP, plus 2 ATP. So overall, the net of glycolysis, net gain from glycolysis is 2 ATP and 1, 2, just 2 NADH. Good. All right, now let's talk gluconeogenesis. So once again, all of these have 2's and 2's all the way up. Okay. All right. So, I also want to mention the amino acids is important because pyruvate can go to make alanine or glutamate and the rest. We're not focusing on them, but they are kind of like alternative pathways if it's already made an amino acid. Just want to point that out. Okay. Anyways, so we've used 2 ATP for the first reaction to convert to oxaloacetate, so minus 2 ATP. Okay. Then we have 2 oxaloacetate going to 2 phosphoenol pyruvate. We're going to use 2 GTP, which once again I'm going to write as 2 ATP equivalent, so just 2 ATP. Okay. It's not exactly the same, but it's very, very close. All right. Next reaction, we get to 2 phosphoglycerate. That's fine. We get to 3 phosphoglycerate. That's fine. Okay. Now we once again use 2 ATP because this reaction is the exact reverse of the glycolysis reaction. Okay, all the way up. Oh, yes, the next reaction, we now lose 2 NADH. All right, and then this no longer involves ATP, this no longer involves ATP. We're done with the energy. So the net loss, the net loss from gluconeogenesis is obviously the minus 2 NADH, and then it's 2, 4, 6 ATP. Okay, so I want us to think about it in terms of if they were reverses, these numbers would add up to 0. Because we cannot do reverse reactions, because we cannot just reverse every reaction, net loss of 4 ATP per 1 complete pathway. So if we went from a single glucose molecule down to 2 pyruvate molecules and then back up to a single glucose molecule, we would have wasted 4 ATP, right? Gluconeogenesis takes energy. Remember, glycolysis was catabolism, we're in anabolism, right? And so because they're different, we lose this energy. I don't commonly see questions about energy asked with gluconeogenesis, but they are absolutely fair game, so be prepared for them. Okay? All right. Then zooming back in. So I think I've mentioned, but I'll mention it one more time in case I forgot. Gluconeogenesis in general occurs in the liver. Now, I've been kind of ignoring locations for a bit, but let's think about it. The pyruvate to oxaloacetate is in the mitochondria. I mentioned that. Then oxaloacetate leaves the mitochondria, so it's in the cytosol. And then cytosol, the reactions going all the way up to glucose 6-phosphate can take place. However, as you can see by the question that I'm just asking here, why does it take place in the endoplasmic reticulum? The reaction to make glucose 6-phosphate back into glucose has to take place in the endoplasmic reticulum. Okay? And the reason it has to take place in the endoplasmic reticulum is that little piece over there. Oh no, okay, there we go. This little thing right here. Okay? This is an ER, or endoplasmic reticulum, associated protein. Not found anywhere else. Therefore, we have to keep everything here. Okay? So, our, I'm at yellow, there we go, glucose 6-phosphate reacts with this, or I should say actually, it's transported in by what they're calling T1, or the glucose 6-phosphate transporter. No energy needed. Okay? Then the reaction happens and you separate glucose into, or I'm sorry, you separate G6P into glucose and inorganic phosphate. Glucose is then allowed to leave through the glucose transporter and then GLUT2 transporter out of the plasma membrane. So this is into the endoplasm, or I'm sorry, into the cytosol once again. This is, inorganic phosphate is in the ER membrane where it can be used for other things. Okay, so it has to take place here because we're dealing with an endoplasmic reticulum associated protein. Okay, now I've just kind of talked about this. The total use is -6 ATP minus 2 NADH. And remember, I include NADH because it's that reducing potential. It's that potential energy that we can use for a net of -4 ATP from glucose to pyruvate and back to glucose, right? So we're going to do a quick recap of the regulation of glycolysis because we then want to talk about the regulation of gluconeogenesis and compare how they're opposite one another. Okay, so first thing you see on the left is glucose 6-phosphate inhibits hexokinase. Again, let's think about why. If you have a ton of glucose 6-phosphate, that's telling you there's a buildup, which is telling you that effectively the first reaction is going a little faster than the rest of them, and it's saying, slow down, we don't need this much, we've already made plenty. Okay, oh, I don't know why it scrolled down, but that works for me because we're there anyways. Okay, so reaction 3, the phosphofructokinase reaction, is governed, or we look at 4 things on the left side. Fructose 2,6-bisphosphate we talked about, that activates PFK. AMP, which tells you you have too little energy, activates PFK. ATP, which tells us we have enough energy, don't make more. And citrate, which tells us we have enough intermediates in the process of getting energy, stop making more, right? The reverse of that. F26BP inhibits fructose 1,6-bisphosphatase because it's saying we have too much, or I'm sorry, we have too much fructose 6-phosphate. We need to keep going with glycolysis, so let's stop gluconeogenesis. And AMP is saying we don't have enough energy. We should not be doing the reverse reaction and wasting more energy. Okay. Then the phosphoenolpyruvate reaction to pyruvate is activated by F16BP. Remember, that's the way that we keep phase 1 and phase 2 of glycolysis kind of matching. Acetyl-CoA and alanine are the immediate, like one step away from pyruvate. So when you have high concentrations of both of them, that's telling you we've made everything we want to make from pyruvate, let's stop. ATP, once again, we have a high amount of energy, stop making intermediates. And then that phosphorylation is about the pyruvate kinase and the, and so, yeah. It's not something that I covered because I've never seen it asked about, but it is there, so let's mention it. All right, the reverse. So Pyruvate carboxylase is activated by acetyl-CoA for the same reason that acetyl-CoA inhibits pyruvate kinase. Because acetyl-CoA is one step away from pyruvate, what it's saying is if there's a lot of it, we don't need to make more of it. We can go backwards. So these are great examples of that reciprocal regulation. And I focus on it especially with phosphofructokinase partly because of the F26BP, but especially because there's so many examples of it there, and it's also just very, very regulated because it is the committing step. But these reciprocal regulations are present pretty much everywhere there is regulation, which I just want to remind you all once again, regulation tends to occur at the very exergonic or the very endergonic processes, because those are the ones for which the reverse is done differently. Okay, all right, so there are the overall processes. Now I wanted to block out some time because I know that this is, exam week, or maybe the exam is next Tuesday. I'm not 100% sure on that. So I want to make sure, does anybody have any questions about content for this exam? So I kind of accidentally went into number 14, which was about the Mwc and Knf models. Those are on this exam. Those were a little while ago. Hemoglobin and myoglobin, fair game on this exam. Let's see, hemoglobin, myoglobin, regulation, carbohydrates, long chains, lactic acid fermentation, stuff like that. Those are all fair game from this unit, and they're all on this exam. So if anyone has any questions, now is a great time to ask it, and I'll go over it in as much time as you want. If not, I'll go over the questions that I made for kind of a very brief review, and we'll call it there. So I'll give you guys a minute to see if you have any questions. Okay, assuming no questions, I will go ahead and I'll start talking about some of the questions that I made. Okay. Oh, never mind. Hang on. Can you go over? Yes, absolutely we can. So I'm going to just answer number 1 first, and then I'll specifically answer the question asked about cooperativity. Great question, by the way. Okay, so let's review MWC and KNF. And just a reminder, the MWC is called the concerted model, and the KNF is called the sequential model. Okay, so, and I remember last time I did this, I used squares and circles, and I used gray and blue and all that. I'm probably going to do something very similar, but just very briefly, the concerted MWC, so I'll do MWC above and KNF below the question. MWC, the way it works is you have what's called the tense state, let's call it that, so T0, and it's in equilibrium with the relaxed state. Okay, so the relaxed state actually has a kind of stable binding site. So assuming that the substrate is that slice of pizza substrate, it can bind to the relaxed state. And the equilibrium that governs this, or I should say the constant that governs this equilibrium, L, tends to favor the tense state. So the MWC model, as we bind to substrates, let's see, as we bind to substrates, we effectively are decreasing the concentration of this, which per Le Chatelier's principle shifts the tense state into more relaxed state, and therefore we can bind more. So that was just very, very briefly the MWC model. Now, to answer the question you asked specifically, can you go over the graphs for cooperativity? So the graphs for cooperativity are kind of that huge diagram that effectively boils down to this, except with a little bit more to it. So let's assume, rather than the drawing that I have, that we have an enzyme that has 2 active sites. And I use 2 specifically because if I draw any more than that, it's going to look 10 times worse, and I don't want to do that. But this can apply to n number of active sites, so just kind of extrapolate from here. Okay, so we're going to redraw this. what happens when enzyme binds to S1? So the first substrate is the exact same thing that I have in green here. The concentration of R0 has decreased. Therefore, since the concentration of R0 has decreased, Le Chatelier's principle disequilibrium moves to the right, and this shows positive cooperativity. Positive cooperativity. There we go. Why does it show positive cooperativity? Because the binding of S1 is not decreasing future binding. Okay, this right here is why it's not. Actually, this might have been the trick question, because I remember there was a trick question on this exam, and I think it might have been this one. I think this is, I don't remember if it's positive cooperativity or if it's like that weird exception to positive cooperativity. So I'm gonna kind of put an asterisk on this one with a question mark. And the reason I put the question mark is because it should be positive cooperativity, but it's not quite, okay? And that's one of also the drawbacks of the MWC model, is that it's very bad at showing both positive and negative cooperativity. It's great at explaining activators and inhibitors in a way that the KNF model couldn't, but it's not the best for cooperativity, okay? Whereas the KNF model is great for cooperativity. So I want to look over that, and I'm going to try to do it in a moment once I get to a pause. But first, I want to make sure. Let's talk KNF model while I'm taking a moment to fact check this. So the KNF model, if we think back to, let's see, let's say there's 4 subunits or 3 subunits. As soon as the first subunit binds to, as soon as the substrate binds to subunit 1 on, so here I'll do KNF. So you have 3 subunits, and we're going to add a substrate, S. That's going to bind to here. As soon as that happens, this thing is transformed. So this is E1 plus S, E1 for subunit 1, S for that. That induces a conformational change in an adjacent subunit. So this is now transformed into the diamond. Okay, and this is E2, this is E3, and then this is still E1 plus S. So I want to point this out, that cooperativity with respect to the KNF model is very straightforward because of this. Because if E2 has a greater affinity for this substrate than E3, that's positive cooperativity. Okay. If, on the other hand, E3 has a greater affinity for the substrate than E2, that's negative cooperativity. So let's think about this. To make sure that's clear, if E2, which has just transformed, if that transformation increased affinity, great, we have positive cooperativity. If it decreased affinity, we have negative cooperativity, okay? So not entirely, it's not super complicated, but it is a little weird, but the KNF model is very clear about cooperativity. The MWC is not the best at it, and that's why I don't want to give you the wrong answer, because I know that there's a weird trick with this, and I just unfortunately am trying to find it. Okay, so give me one moment while I pull that up. I apologize. I have it in my notes somewhere. It's just taking me a minute to find it. Okay, so I don't like these explanations, though. They're not quite correct. Okay. So the MWC model is, yes, okay, I knew there was a trick to this one. The MWC model is basically negative cooperativity, all right? While to some extent, the binding of, or I should say the highlighted yellow with Le Chatelier's principle is making up, or is kind of helping us get to more R0. Ultimately, it's not going to give us the exact same amount. So if we started with, let's say, 100 and 100, and we bind 10 of them, so we're left with 90 now, we're never going to go back up to 100. We're only ever going to get to maybe 95 and 95, just for a very simple example. And so because of that, subsequent binding onto R0 is less favorable. But also, how much more favorable is binding to R1 than R0? It's not really. And so I should say to, sorry, give me one moment. Like that, something like that. So S1 and S2, which makes this R2. This is never really defined as favorable. Is it favorable? Favorable. The answer to it is, it really depends, but generally no. And the simple reason for that is because with all of these, we'll switch colors. With all of these equilibriums going on, as soon as you pull from one, you pull everything else toward it. So as soon as you get more binding to R1, or hang on, let's do this in red. So as soon as the concentration of R1 increases, and that happens, well, what's going to happen? This goes this way to compensate, and then this to some extent goes this way. But let's say we now bind to, sorry, trying to switch colors to keep things pretty consistent. We now bind to an activator. So this is R1A. Well, that decreases this, which pulls this way and pulls this way. And so it becomes this kind of complicated web of just a mess. And that's why cooperativity here is very painful to talk about, because you can show positive cooperativity in the same way that we show in hemoglobin, with the tense versus relaxed states, but it's really positive cooperativity in the way that the Knf model has it. And so the answer that I'm going to give you is the MWC model is not good for cooperativity. And that's part of the reason that Knf model exists, is because it's better at representing cooperativity fairly. But yes, so that's kind of the gist of it. So I think a very common question that gets asked is, does an inhibitor or an activator or whatever cooperativity? The answer is no. Excuse me. The actual binding of an inhibitor or of an activator is not going to increase or decrease cooperativity at all. Okay? That's one of those other weird topics. I don't know if that fully answered your question. Unfortunately, this is one of the topics that, you know, different people can argue different points, and so it's not always clear. So I can't give you a better answer than this, and I apologize. Okay. So we're going to move into number 2, though, because I think that the topic on hemoglobin is also very important to review with respect to cooperativity. Okay, so once again, quick reminder, here we go. Hemoglobin has 4 subunits, 2 alpha and 2 beta, and this is the color coding that I'm going to be using. Okay, good, I'm glad, and again, I apologize. I wish it was a better explanation. There just really isn't a good one. All right, so those are the subunits. The first thing that happens is the first subunit binds to the first oxygen. The first one that binds is an alpha subunit. Okay, so binding is going to be a filled, excuse me, A filled circle or square is going to be oxygen is bound to it. Okay, nothing else changes. Right? The first change that now happens is KNF. Okay, and what I mean by KNF is the binding of the first oxygen affects the adjacent alpha subunit and makes it more favorable. Okay, so therefore it transforms from a square to a circle. Okay, and the beta subunits are unchanged. Now I'm going to pause for a moment and I'm going to refer back to these things that I just talked about because I'm going to have to erase them in a moment. What we're seeing here is the induced change is better than the initial state. Therefore, this is A, positive cooperativity, and B, it's this exact example that I drew right here. E2 is greater than E3, therefore, we are increasing substrate binding. Okay, now I have to erase these for space, but I hope that made sense, and I can redraw them later if anyone has questions. Okay, all right. So now the next step of this is, once again, O2 binds with, it preferentially binds actually, because now there's a high affinity for it among the new subunit. Okay, awesome. All right, the beta subunits are once again unchanged. All right, this is the last time I'm going to be saying that, because now the beta, this is considered the tense state of this equilibrium, and we're in the MWC model. Okay, so directly below, or actually above, I'm going to say MWC, and the relaxed state, which I'll label with green, is going to be an induced conformational change in both beta subunits at the same time. Okay, subunit 1 and subunit 2, and then both beta subunits are now circles. Once again, the circle is preferentially binding to oxygen over the square. Okay, so I want to point out this happened subunit by subunit because it's not the concerted model, it's the sequential model. Sequential. This happened all at once. All at once, just like the concerted model says it will. Okay, and then I'm not going to draw the last steps, but basically these two bind to oxygens and we're happy. Okay, so that's how hemoglobin shows first the KNF model with its sequential conformational changes of subunits and its positive cooperativity. Then the MWC model is concerted. Now, in terms of what's actually happening, like to hemoglobin, the first conformational change is basically the iron coming back down to within the plane of the rings. The second change is when you have that second oxygen bound, that induces about a 15-degree rotation in the beta subunits, which opens up their active sites. Okay, that's the technical stuff. I personally like showing the MWC and KNF model. All right, why are metabolic pathways regulated? Or where are metabolic pathways regulated and why? So the where is highly exergonic, and in terms of the reverse, it would be obviously endergonic if we're thinking of it. Reactions, and at reactions differing between the forward reaction and the reverse reaction. Okay, so we, in the case of glucose and gluconeogenesis, glycolysis and gluconeogenesis, we do not regulate the phosphoglucoisomerase reaction because it's energetically neutral, and it's the same for both the forward and reverse reactions. We will regulate 1, 3, and 10 because those are both highly exergonic for glycolysis and different between the two. Now, in every case that we've talked about, the reactions that are different are the highly exergonic, but I want to list both just in case because I'm sure there are exceptions that I don't know about. Okay? All right, number 4. Is this an aldose or a ketose, and how can you tell? So what we do is we look for the carbonyl. Just a quick recap, the carbonyl is the double bond to the oxygen. If that carbonyl is at the end, it's an aldose because that means that it would have a hydrogen. If it's not at the end, we have a ketose. This, because it's got carbon on either side, is a ketose. Okay. Now I want to also mention numbering while we're here. With an aldose, you number from the aldehyde, and you go 1 all the way down to however many you have. With a ketose, you number from the side closest to you, or closest to the ketose. So this carbonyl is closest to this end, therefore this end is 1, 2, 3, 4, 5, and 6. Okay, and that's how we tell, and that's the numbering. Okay, and then on the same question, is this an L or D isomer? And draw the other isomer. So the way that we do that is we look at the last chiral center. So carbon number 6 is not chiral because it's got 2 hydrogens, and to be chiral, you have to have 4 unique substituents, which means carbon number 5 is chiral. Or I'm sorry, which means carbon number 5 is the last chiral carbon. Okay, so when we look at carbon number 5, we see there's the OH to one side and the H to one side. So and once again, the way I do it is I say left is L, R is right, I'm sorry, D is right, and that's with respect to the OH. So if the OH is on the left, we're looking at an L isomer. If the OH is on the right, we're looking at a D isomer. Therefore, this is the D isomer. And we can confirm this because this is D-fructose, actually. Okay? Now there's one more bit that we have to do. We have to draw the other isomer. So, common misconception, let's just flip these two, call it a day, we're done. That is wrong. Okay? The reason that is wrong is because L and D isomer are enantiomers, which makes them non-superimposable mirror images. Superimposable mirror images. Now that's really wordy, and that confuses me. So I think of it as flip every chiral center. Okay, so in other words, to draw L-fructose, we have to say, okay, carbon number 1, is it chiral? No, because it's got 2 hydrogens, it can stay the same. Carbon number 2 is the carbonyl, it's got a double bond, it's not chiral. Carbon number 3 is chiral, we have to flip its chiral center, and we do that by just flipping the H and the OH. We do the same with carbon number 4. And we do especially the same with carbon number 5, which governs whether it's the L or D isomer. And carbon number 6, as I mentioned earlier, is not chiral, therefore it stays the same. Therefore, great way to check it is look at that last chiral carbon. It is in fact an L isomer. Okay, and I think there are 2 more questions, which I think I can get done in the next 3 minutes. Let's do it. So what is the difference between amylose and amylopectin? So I'm just going to go ahead and just give the answer right now. The answer to this is D, and then let's talk about it. Amylose is straight chain. This is amylose. You have a glucose here with its carbon number 1 and a glucose here with carbon number 4, and they are bound together in an alpha 1,4 glycosidic linkage. Okay, and the same thing keeps going on, alpha 1,4, all the way around. Okay, so now I'm going to draw a dotted line, and I'm going to say, well, what is amylopectin? Amylopectin is the exact same in terms of the alpha 1,4 glycosidic linkage, except in position number 6, which remember is sticking out, you've got an alpha 1,6 linkage. So now we draw this, and then this is still 1,4s all the way around, and then maybe there's another branch here, and maybe another here, and so on. Okay, but effectively, amylose is the straight chain, amylopectin is branched. Okay, and a quick recap: alpha 1,4. Alpha refers to whether it is this is alpha. Beta looks like this. And that comes down to basically the position of the oxygen. And okay, so that's that. 1,4 refers to the carbon number. So looking at glucose, and I'm just going to very quickly draw this. It's 1, 2, 3, 4, 5, and 6. So that's where that comes from. And this is actually glucose alpha 1,4 glucose to be more thorough. So yeah, okay. All right, and number 7 with just enough time to answer it. Why would we choose lactic acid fermentation when the Krebs cycle and the electron transport chain give way more energy? And so I did talk about this earlier last week, but I'm going to do it once more. We start with glucose in both cases. I'm going to ignore it. I'm basically going to ignore everything that's either a duplicate or a big organic structure. So I'm going to ignore these. I'm going to ignore ATP, water, and H+, ATP, water, and H+. Okay, and here's the difference. When we go to pyruvate and stop, so reaction 10, we make NADH. More importantly, we deplete NAD+. So when our body is lacking oxygen, we go to lactate in order to confirm that we can, or in order to regenerate our NAD+ stores so that we can keep doing glycolysis to get energy rapidly without the need of oxygen. Okay, replenish NAD+ for more glycolysis, because remember that the electron transport chain is an aerobic process. We need oxygen for it. Therefore, we don't have oxygen. So for exercising, working out, and it's an intense workout, we use lactate instead so that we get more NAD+, because glycolysis is the best we have in terms of making energy. Okay, and I am kind of pushing it on time, so I apologize, but good luck on your exam, everyone, and I hope we see you next week. And yeah, that's it. Have a great week.